Hi boys and girls. Today we begin Unit 7, Differential Equations and Applications of Integration. Our first lecture, 7.1, is entitled Slope Fields and Euler's Method, and this will be part 1 of that discussion. A differential equation in x and y is an equation that involves x, y, and derivatives of y. Here's an example. Y prime plus 2y equals 0. Notice it involves a function y and the first derivative of that function. A function y equals f of x is called a solution of a differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. So let's see how this works. Is y equals e to the negative 2x a solution to the differential equation y prime plus 2y equals 0? Notice the differential equation has y, the original function, and y prime, the first derivative of that function. So let's find the first derivative of our function y equals e to the negative 2x. Y prime is equal to e to the negative 2x, of course, times the derivative of negative 2x, which is negative 2, and that can be written as negative 2 e to the negative 2x. So if y equals e to the negative 2x is a solution of this differential equation, I can replace y with the original function e to the negative 2x and y prime with the first derivative of that function, negative 2 e to the negative 2x, and this will make a true statement. So let's see if that happens. Y prime, negative 2 e to the negative 2x, plus 2 times our original function, e to the negative 2x. And of course the question is, does that equal 0? You can see, of course, that it does equal 0, which means then that y equals e to the negative 2x is indeed a solution to this differential equation. In the previous example, you may have realized there could be more than one solution to a given differential equation. So in this example, we're going to determine whether each of these three functions is a solution of the differential equation y double prime minus y equals 0. After all, we just need to find a function such that its second derivative minus the original function equals 0. So let's try this first example, y equals sine x. We're going to need the second derivative and the original function. So the first derivative is y equals cosine x. The second derivative, y double prime, is equal to negative sine x. Now let's take the two parts that we need, which are y double prime and y, plug them into this differential equation and see if it makes a true statement. Negative sine x minus sine x, and the question is, does this equal 0? And of course that answer is no. If this had been y double prime plus y, we would have seen that it would make a true statement. But the way this differential equation is set up, then no, y equals sine x is not a solution of this particular differential equation. Let's try our second example. We'll need the second derivative, so let's go ahead and find the first derivative, y prime 4e to the negative x, and then times the derivative of negative x, which is negative 1, and that means we would have y prime is equal to negative 4e to the negative x. Now let's find the second derivative, y double prime negative 4e to the negative x times the derivative of negative x, which is negative 1, and this gives us y double prime is equal to 4e to the negative x. Now we'll need this piece and this piece to plug into our differential equation to see if it is a solution. So we're going to say the second derivative, 4e to the negative x, minus the original equation, 4e to the negative x. And of course the question is, does that equal 0? And indeed, yes it does. So we have found a solution. Y equals 4e to the negative x is a solution of this particular differential equation. Now let's try the third one. Y equals ce to the x, where c is representing any constant. The first derivative then, y prime, will be ce to the x. The second derivative, y double prime, will also be c e to the x. We'll need the second derivative and the original function in order to determine if this is a solution for the differential equation we've been given. The second derivative, c e to the x, minus the original function, c e to the x, and the question is, does this equal 0? Of course we see that it does, which means we have found a second solution for this particular differential equation. There could be more, the idea being that any function such that the second derivative minus the original function equals 0 would be a solution of this differential equation. The order of a differential equation is determined by the highest order derivative in the equation. For example, y prime equals 4y is a first order differential equation, since the highest derivative in the equation is a first derivative. Y double prime minus y equals 0 is a second order differential equation, since the highest derivative in the equation is a second derivative. 2y minus y triple prime equals y prime is a third order differential equation, since the highest derivative in the equation is a third derivative. Geometrically, the general solution of a first-order differential equation represents a family of curves known as solutions curves, one for each value assigned to the arbitrary constant. For example, y equals c over x is a solution for the differential equation xy prime plus y equals 0, and depicted here are 4 of the solutions curves corresponding to different values of c. We have -2, -1, 1, and 2. But since there are an infinite number of possibilities for c, this means there would be an infinite number of solutions curves for this differential equation. From an infinite number of solutions curves, we may be interested in narrowing it down to one particular solution. For example, this graph depicts the family of solutions curves for y equals cx squared, but we might be interested in the particular solution that goes to the point 1, 3. Particular solutions of a differential equation are obtained from initial conditions that give the values of the dependent variable or one of its derivatives for particular values of the independent variable. The term initial conditions stems from the fact that often in problems involving time, the value of the dependent variable or one of its derivatives is known at the initial time t equals 0. For instance, the second order differential equation s double prime of t equals -32, we recognize this as our acceleration function, having the general solution s of t equals -16t squared plus c sub 1t plus c sub 2, a general position function, might have the following initial conditions. S of 0 equals 80, meaning initial position is 80. S prime of 0 equals 64, meaning initial velocity equals 64. In this case, the initial conditions yield the particular solution, S of t equals -16t squared plus 64t plus 80. For the given differential equation xy prime minus 3y equals 0, verify that y equals cx cubed is a solution, and find the particular solution determined by the initial condition y equals 2 when x equals -3. So this problem is asking us to do two different things. First, verify that this function is a solution for this differential equation. For that, we're going to need the original function and its first derivative. So we have y equals cx cubed. The first derivative then will be 3cx squared. That means we need x times the first derivative, 3cx squared, minus 3 times the original function, cx cubed, to equal 0 for this function to be a solution of this differential equation. When we simplify, we see that we have 3cx cubed minus 3cx cubed equals 0, a true statement. Therefore, we have verified that y equals cx cubed is a solution of the differential equation xy prime minus 3y equals 0. but this is a general solution and it would generate a family of solutions curves. So now we're going to find a particular solution determined by this initial condition when y equals 2, x equals -3. Y equals cx cubed. The general solution. Now let's replace y with 2 and let's replace x with -3 to solve for a specific c. This means 2 equals c times -27, and when we divide both sides by -27, we get that c is equal to -2 over 27. Therefore, our particular solution will be y equals -2 over 27 x cubed. That's it for today's lecture. I don't know if you've played this game lately, but it seems to have gotten a bit more complicated. Hopefully, you'll find this diagram helpful. God bless you, boys and girls.